Hello, everyone, and welcome to Coffee with Caleffi. Today, our topic is optimizing mixing valves in domestic hot water systems with Cody Mack. So he's going to be doing the presentation today. He's been in the business for over 20 years and has a great mix, I think, of hands-on experience, used to be a service tech, and then also can really get into the weeds with the engineering stuff, which is what we're going to cover today. So if you are having issues with the audio, you probably can't hear me right now, but hopefully you see that tech support number right there. You will get a copy of today's presentation if you want it. So in the post webinar survey, just hit yes. And then we also archive these on YouTube, so you can also see over 12 years of Coffee with Caleffi on the YouTube channel. Here's what the certificate of attendance looks like. And then we'll send you that, and it may work in your state or province depending on the local rules. So as you probably saw in the video, we won the AHR Innovation Award for the angle mix in 2021. So we didn't have an AHR show in person, but this really cool product of ours took home the blue ribbon. So we're very excited about that. And then hydronics is out now. So issue 28, contemporary hydronic cooling for commercial buildings. Hard copies have been sent, and then also we do, on the next slide, have digital editions too. So this is not just a PDF that you download, but it's more of an interactive feature on the website that you can see different resources that relate to the topics and things like that. So an alternative to the hard copy. And on Monday, tune in to see Cody and I fight after the showdown after Shop Talk. So my dad's going to cover pressure reducing valves and all the things that relate to that. We'll have some live video to show the product in action, and then we also have a giveaway. So Knipex has donated some pliers and some three-piece sets that we're going to be giving away to attendees, so make sure you sign up for that. And next month, John Siegenthaler will be back to do an extended 90-minute edition of Find It and Fix It. So he's going to look at different piping diagrams and figure out, okay, what's going on here? How can we pipe this better? What would we add? What we change to make the system work right? So that'll be a nice, fun, interactive one that you can play the game of Clue with. So that'll be good. And then I will turn it over to Cody. So take it away.
Perfect. Thank you very much, Max, and happy Thursday, everybody. Thanks, everybody, for joining us. I would like to think that we really hit a nerve with this particular topic today with mixing valves. You know, it seems like I talk about mixing valves every day, you know, and at Caleffi, we make a lot of different mixing valves. We sell a lot of different mixing valves. We get a lot of calls about mixing valves, and really with today's webinar, what we wanted to do is basically just kind of dispel a lot of the thoughts, or incorrect thoughts or misconceptions that we see, a lot of the improper applications that we see with mixing valves. And first and foremost, I just want to just go over the fact that it's just a really basic device. You know, you're taking hot water, you're taking cold water, and you're producing a stable mixed outlet temperature. Hopefully, okay, that's the big if there is hopefully. But there's a lot of things that, despite being a very simple device, can really make your life very, very miserable, whether you be an installer, a service contractor, or a designer. And there's things that you just really need to watch out for. So we wanted to talk about all these different topics here today to again, go over what you might run into, how to prevent it, how to see it before it gets you, or before it blindsides you, and we want to try and get through all this guy here today. We did have a lot of great questions that were pre-submitted on the registration for the webinar, and if you have any questions today too, don't hesitate to put them in that questions bar within the GoToWebinar software. Whatever questions that we don't answer today, we will definitely I will get back to you personally on all those questions. But again, a lot of great questions that came in, and we appreciate the thoughts on that, because again, like I said, we must have struck a nerve here a little bit, but it happens. So the first thing I want to start off with is the idea that people make mistakes, okay? I came from the service side of the industry. I'm not going to tell you that I never made a mistake, because I did. I diagnosed the wrong thing. I thought it was this when it turns out it was that. And I just want you to think about a time, and this is a semi-rhetorical question, but if you want to type something in, if you want to let us know some experiences that you've had, definitely do that. But like I said, kind of a semi-rhetorical question. The fact that the mixing valves, in a lot of cases with domestic hot water systems, they have a tendency to get a bad rep. And it's not necessarily because the mixing valve's at fault, it's because of something else within that system or that application that's causing things to go a little haywire. And again, we want to try and dispel those rumors. We want to try and clear up those misconceptions and make sure that you're rip roaring and ready to go. So the first thing I want to talk about is recirc creep. And recirc creep is one of those things that happens, and you may not have heard this particular terminology or this particular idea, okay? But what I wanted to start off with was the symptoms. And the reason why I wanted to start with recirc creep first is not only can it be problematic, it can make you think your mixing valve has gone bad or something's going wrong in the system, but it's also a potentially dangerous situation for the occupants of the building. And so not only can it just cause you callbacks and things like that for your service contractors, but it can cause lawsuits and all kinds of other not so fun stuff. And so what we want to do is go through the symptoms with recirc creep, because you may have already experienced it and you don't even really know how to kind of put your finger on it. It's something that you're not exactly sure what happened. Okay, so what you're typically going to find is you've got a domestic hot water system with a point of distribution mixing valve, and what you're going to have is typically long periods with little to no demand from the domestic hot water system. And then you're going to have a recirculation system in there as well. And what you're going to find is whoever opens up that first faucet in the morning, because typically this long period of no demand is going to happen overnight, whether it be a nursing home or a healthcare facility, things like that. But the first person that opens up that faucet in the morning is going to see some incredibly hot water, okay? Incredibly hot water to the point of scalding. And what you're going to find there, when you talk to those building maintenance people, is that, yeah, they get this incredibly hot slug of water out of this domestic hot water distribution system. But then the rest of the day, everything works great. And it's like, well, how can you explain this? This is the strangest thing. It does this once a day. It's like clockwork, and then everything works great. And so we're going to talk about how recirc creep actually happens. And so we talked about the symptoms. We're going to talk about how it actually happens, and then we're going to talk about how to fix it and how to prevent it from actually happening. We've got a couple of solutions there for you. So again, you're going to need a domestic hot water distribution system. You're going to need a point of distribution mixing valve, like what we've got up here on top of this tank of this very, very simplified drawing here. And again, you're going to look at continuous recirculation, meaning that recirc is running 24 hours a day, 7 days a week without stopping, okay? And then the last piece of this puzzle is the fact that you are going to have this long period of no demand from your fixtures. So again, typically overnight, or maybe the building's unoccupied for the weekend or for a day, for a holiday maybe, things like that. And the scenario here is that during that time of inactivity, the mixing valve's not getting cold water anymore. Okay, your recirc, which if it's sized appropriately, that's a whole nother ball of wax to go into, a whole nother tangent to go down, or road to go down. But if that recirc is sized properly, balanced properly, and everything like that, you're typically going to be seeing about a 5 to 10 degree temperature difference on the recirc coming back versus the mixed outlet going out to that building. So just for round numbers, say you're distributing 120 and you're getting roughly 110 to 115 coming back. And what you're going to have here is that recirc's coming back, and now it has the ability to either go into the cold inlet of the mixing valve or down through your domestic hot water source and then back to the hot inlet of the mixing valve. And the entire reason behind recirc creep actually happening, to where that distribution system and the recirc line can come up to an incredibly high temperature, is the fact that the mixing valve is not going to be capable of completely shutting off one side or the other. Okay, now I'm going to say it right here and right now that ASSE 1017 does not require you to have the ability to completely shut off the hot or cold inlets. This is very different from your ASSE 1070 mixing valves, which are going to be your point of use mixing valves. Those do have the ability to completely shut off the hot inlet in the event of a cold water failure, but 1017, that's not a requirement. So again, you've got your recirc coming back 110, 115. Most of it's going into this cold inlet, but some of it's going to go back through this tank, and it's going to come back to this hot inlet. And the issue lies in the fact that in certain scenarios, the mixing valve is not going to be able to close down completely, and actually just not enough is what it boils down to. So what you have the ability to do in that scenario is, if this hot inlet's open a little bit more than it needs to, you're going to have the ability to add more heat to the loop than what the loop is giving off. Okay, so if you're storing your domestic hot water at 140, 150, 160, whatever you're storing it at, okay, really, when you've got 115 coming back to the cold inlet and you want 120 coming out of here, you only need that tiny little bit of heat to bring that loop back up to temperature. And again, if this can't close down enough, you've got 150 or 160 degree water coming into there, and again, sooner or later, it's just going to start adding and piling on. And if you leave it go long enough, it can actually run up that distribution system in the recirc line all the way up to whatever you're storing that tank to. And again, whoever opens that first fixture, big surprise, hopefully no scalding, but then it's going to work perfectly the rest of the day, because again, you're going to have that continuous demand throughout the day, whether it be washing hands or showers or whatever the case may be. So this diagram here is, again, very simple diagram. This is what we typically see out of your domestic hot water recirc tie-ins and everything like that back at the water heaters. But we've got a couple other ones here too, and I just want to address them real quick before we move on. The second one is if you have a tapping on your tank, okay, and then it'll even be labeled right on there, recirculation tapping or recirculation connection, things like that. It'll be typically about midway up on the tank, okay. Now, if you did not have a mixing valve, okay, that tapping would be perfectly fine, okay? And you might even see in some scenarios where you're tapping into the bottom of the tank, and it's the same scenario. If you're doing either mid-tank tapping or at the bottom of the tank tapping, if there was no mixing valve, everything would be just fine, okay? But in many cases, mixing valves are a requirement per code for commercial buildings and things like that. So you have to have them. So the issue here is if you've got that mid-tank tapping or at the bottom tapping at the cold inlet or at the drain, now all of a sudden, instead of 115 degrees coming right back to the cold inlet up here, that 115 degree water has to come into the bottom or to the midpoint there of the tank. Now it either has to travel backwards up through the dip tube or through the hot inlet or the hot outlet of the tank to the hot inlet of the mixing valve. And what you're actually going to have the ability to do by traveling backwards up this dip tube is, again, through the stratification of the tank, you're actually going to be adding more heat to that recirc. So you're going to need even less heat to bring that loop up to temperature to make sure you're maintaining that 120 degrees. Okay, so it's something that I would say with a mixing valve application, if you're piping it like this, I would try to avoid it. And I've got some other scenarios and other piping diagrams going forward here that will make more sense of why you would actually need to use that recirc tapping or that bottom tapping there too. So so from there, again, we're going to go back to that first drawing, because again, most common and everything like that here. And we're going to talk about, again, the fact that the recirc's coming back. It's going to go down the cold inlet. It's going to either go to the cold inlet of the mixing valve or through into the tank and back around again. Okay. Again, the mixing valve, if it doesn't have the ability to completely close off, it's going to add more heat than what it's giving off, and you're going to have some problems. Now, you might be thinking to yourself, Cody, I've got a very simple solution to this. Okay. It's an aquastat. Okay, perfect. I can fix this problem. Okay, I can spend $20 on this aquastat, and I'm never going to run into recirc creep again. Okay, but I want to caution you on that, and I will preface that by saying there are many mixing valve manufacturers that not only recommend but even require aquastats. There are a lot of municipalities as well, certain states that come to mind, California, that require aquastats. And the idea with a lot of the requirements by the AHJs or the local municipalities is that they're trying to save energy. Totally get it. Okay, you want to save energy by turning off that recirc. If the loop's up to temperature, why on earth do we want to keep running that recirc? Okay, but again, there's got to be a trade-off here. There's always a downside. There's always something you got to watch out for. And I would say the biggest thing that we're talking about going forward in the future here is by turning off that recirc, you are creating a perfect breeding ground for Legionella bacteria. Okay, and we keep hearing about Legionella over and over again, whether it be cooling towers or domestic hot water systems, potable water systems, things like that. But Legionella bacteria is looking for not only warm water typically, but it's looking for stagnant water. So if you are running that recirc on a timed event, you know, to where during unoccupied times it's shutting off, or it's on an aquastat, again, you're creating that perfect breeding ground, because the Legionella bacteria is looking for that 70 to 120 degree water, and it's looking for stagnant water. And again, stagnant is the key term here. So by keeping that recirc on, you can eliminate that stagnant water scenario, and you can help to basically kind of manage that Legionella risk to an extent. Okay, and I hope and it's one of those things that I hope going forward that that a lot of those requirements for aquastats will be abolished. And I'll give you a little fun fact. I actually talked to a guy from California. He said he was running continuous recirc at one point, and I said, well, wait a second, you know, like, I thought you were supposed to have an aquastat on every single one of your recircs and everything like that. And he laughed and he goes, oh, of course, yeah, they require aquastats. And I'm not going to name this guy's name. I don't even remember it, to be honest with you. But he said, of course, they require aquastats, but they don't tell you what temperature to set it to. And I said, you are a genius, sir. The fact is that he put an aquastat on there. The inspector's happy. He set that aquastat to 180 degrees, and the recirc never shut off. Okay, so you know, do what you got to do in certain scenarios. I totally get it. But again, the fact is that, you know, aquastats, you know, while being able to prevent recirc creep by shutting off the recirc if it gets to a certain temperature, may lead to other issues that you're unaware of. Okay. So here's another quick visualization on recirc creep, just to kind of give you it in a different form here. Okay, so in the upper left over here, you're going to have your stable operation. You're going to have high demand or moderate demand from your domestic hot water system or from your fixtures, and you're going to have cold water coming into the cold inlet, hot water coming into the hot inlet, and you're going to be maintaining that stable desired mixed outlet temperature, and that's perfect. Okay, but then sooner or later, you know, everybody goes to bed, or the demand from the potable system or domestic hot water system goes way down, and sooner or later the mixing valve is just working with the really hot temperature from the domestic hot water source and the pretty warm temperature from the domestic hot water recirc. And so the mixing valve can handle this for a certain amount of time. Okay, it's going to do its job. It's going to try and do its job the best it can, and you'll notice it's still maintaining. But sooner or later, you know, that recirc is going to start coming up in temperature a little bit, and you're going to notice the mixing valve is going to want to try and clamp down on that hot inlet, but it can't. It physically can't shut it down all the way, and you'll notice that your mixed outlet's going to start coming up in temperature. And again, as that temperature starts coming up, the mixing valve again tries to clamp that hot inlet down as much as possible, but it can only do so much. Okay. And again, if you let it go long enough, it will come up to whatever temperature you're storing that tank to. And that is a big problem, because again, if you're 140 is one thing, but you see some of these applications where they're storing at 160 or even higher, that is like instant scald kind of capabilities. And it's something that, again, you know, scalding can actually lead to death in a lot of cases, just due to a lot of other circumstances. But it's obviously something that you want to avoid. And again, if you guys have questions, don't hesitate to type them in there too. So let's go over a couple scenarios on how to fix it. Okay. The first one that I want to go over here is a real basic piping diagram, and this is actually shown in our technical brochure for our high flow thermostatic mixing valves. And what you'll find here, and accompanied with this nice diagram, is a really detailed outline on how to properly pipe it and balance it accordingly and everything else. And what you're going to see here is, instead of the recirc coming back and just tying in at the cold inlet of the mixing valve, you'll notice that the recirc comes back and it ties in at the cold inlet, but it also goes right around and connects to that domestic hot water source. Now, if you don't have a tank tapping, you might end up coming right down here to the cold, right at the cold inlet of the mixing valve. But along with that splitting of the recirc, what you're going to have here is two valves, and you'll see them circled here in purple. Now, these are going to be control valves. I'm going to highly recommend using globe valves in this scenario. However, any valve is better than no valve, okay? But just remember, globe valves are a good control valve. They're, you know, versus a ball valve or a gate valve that's really just meant more for shut-off type applications. But with these valves here, what you're going to essentially be doing is overriding the control that that the mixing valve has during times of no demand. Okay. So what you're going to do here is for this valve going back to the cold inlet, and you'll notice too here that there's a check valve right upstream on the cold side, so that this line here, it has to go through the cold inlet of the mixing valve. It cannot go backwards through the tank, to the hot inlet. And what you're going to do with this valve number 2 is you're going to leave this valve completely wide open. Okay, and then valve number 1, what you're going to do with this valve is you're going to open up this valve just enough to maintain or add enough heat to the loop to maintain the temperature of that loop. So you're just, there's no specific flow rate that you're going to be looking for. I mean, I'm sure you could figure it out if you do all the math, but it's a very trial and error type process. And I say how to do this in about 30 seconds, but it's, in all reality, it's a pretty lengthy process. It's just like every project my wife wants me to do at home. It's really easily said, but not easily done in many cases. Okay, so with that in mind, you're going to want to set this valve here, valve number 1, to just basically eke by enough flow through there to go through the tank, and then add just enough heat back into the mixing valve to bring that loop back up to whatever temperature you want it set to, so 120 degrees or whatever. But you're going to need a very specific scenario in order to accomplish this. You're going to need your domestic hot water system up and running. You're going to need a fully functional recirc system that's perfectly balanced like it should be. And then from there, you're going to need a time where you have next to no demand or no demand from your domestic hot water system or your potable water system. So you're either going to be doing it while the building's completely unoccupied or in the middle of the night and things like that. So it really turns into a kind of an interesting story and an interesting thing, because it's kind of difficult to do, because again, you've got to have this really specific set of circumstances. Okay, so this is how you would do it though. This is a really interesting scenario where this is how you can fix recirc creep by basically, again, overriding the mixing valve, because again, per ASSC 1017, they're not required to have those mixing, and this isn't just our mixing valves. I'm going to say this is everybody's mixing valves, but per ASSC 1017, it's not a requirement to be able to completely shut off that hot inlet. Okay, so we call this out instead of an aquastat in order to maintain that loop temperature without creating recirc creep and things like that. So again, really interesting scenario, but hopefully you guys can latch onto that one. So there is one other option though. There are actually a couple of mixing valves, and some of which that we actually create, that do have the ability to completely close off that hot inlet to prevent recirc creep. Okay, one of which is our AHR award-winning angle mix here. This uses a very interesting cartridge technology that's very fast reacting, and again, it does have the ability to completely close off that hot inlet. And you'll notice that the hot inlet and the mixed outlet are right in line with each other, so it makes piping really, really easy. Very, very cool valve. Here's just a little bit of the testing that we were doing at the lab here in Milwaukee. You'll have to forgive the black iron fittings. They're just cheaper than low lead stuff, and it's all non-potable anyways. So from there though, this guy is a good valve for, again, your smaller, your residential, light commercial applications. It's available 1/2, 3/4, and 1-inch connections. But then if you're working in commercial applications, which is where you're probably going to see more of your continuous recirculation than your smaller residential and light commercial stuff. But if you are working in those commercial applications, we've got our Legio mix. This is our electronic mixing valve, and I know there was some questions in the pre-submitted about thermostatic versus electronic and things like that, but I want to talk about how this guy can prevent recirc creep. Because of the fact that it is a 3-way ball valve assembly, it can actually give you bubble tight close off on either side, hot or cold if necessary. So you don't have to go through all the trouble of the globe valves and the balancing in the very specific scenario where you've got no demand from your fixtures. You can just pipe this in and you're good to go. It's really straightforward. But as far as just some differences that you're going to find between thermostatic and electronic, that was a big question that came up multiple times in the pre-submitted questions. The biggest thing you're going to run into here is the ability to connect to building management systems, which is growing more and more of a requirement in a lot of commercial buildings. Some are requiring electronic mixing valves so they can be set, they can be monitored and things like that. Our control here for the Legio mix also has the ability to do data logging just on its own. It can do 40 days worth of data logging, but then again, you connect that up to building management systems, you can do even more extensive data logging. You can do trends and things like that to see exactly what's going on with that mixing valve, and it's a great troubleshooting tool as well. So so just some brief differences there, but they're both ASSE 1017 mixing valves. They're both going to be able to control the temperature just as well. But the nice thing about these ones, on top of all the features that we mentioned, is that they can completely eliminate recirc creep altogether. But we had an interesting scenario here just recently. Let me see if I can go to the next slide there. Perfect. We had an interesting scenario where we weren't running into recirc creep, but we were running into the complete opposite. Okay. Instead of recirc creep, where it was creeping up in temperature on that loop, during times of no demand, they were actually running into problems where the loop temperature would drop. Okay, and obviously that's a problem as well. If you've got a big distribution system and that recirc temperature drops and drops and drops, and then sooner or later somebody starts opening fixtures, and it takes a long time for the hot water to get there, you're going to run into some unhappy occupants in that building. And so what you're going to find here with this particular guy is the recirc is going to come back, and it's going to go into this T right at the cold inlet, and the only place it can go is to the cold inlet of the mixing valve, because they had a swing check that was installed right just upstream, which is very similar to the drawing that I just showed you. Okay, but in the drawing that I just showed you, the recirc actually tied in right here and went back to the domestic hot water source. And so when I got this call, I said, you know what? I said, really, you should be looking at tying in from the recirc back to the domestic hot water source, or coming back from the recirc outlet there on that circulator back to the cold inlet of the domestic hot water source. But you know what? Sometimes you just got to do what you got to do, you know. It's something that it's not always the most ideal situation, but another way that was going to work is the fact that they were actually able to completely gut out that swing check that was in there. So they opened it up, they gutted out the swing check. Somebody got out their magic marker and wrote, you know, removed, you know, check valve from the swing check, and now what they have the ability to do is go backwards during times of no demand, backwards to that cold inlet of the mixing valve, down in through the tank, and then back up through the tank to go all the way back to that hot inlet. So now they're not going to run into recirc creep anymore, or recirc droop anymore, because the mixing valve is going to be able to add heat to that loop, again, by going backwards through that tank and all the way back around again. So it was a bit of a maze, but it was an easy little fix, and it even coincides actually with some of the drawings that we have put together. So that's just one of those little things you got to watch out for. A check valve in the wrong place in any scenario is going to be a real problem. But like I said, this is a scenario that we actually call out on our diagrams. Now, our Legio mix here, we actually take this diagram here and we help you to learn Italian because it's bilingual here, but we also zip tie this to every single Legio mix valve body. And it's got two different piping diagrams on there. One for a smaller domestic hot water system without a recirc connection on the tank, and then one with a recirc connection on the tank. And you'll notice here, it's just like what we did in that last picture where we gutted that swing check. So now it can go backwards through this cold inlet of the mixing valve, and then back to that domestic hot water source, and then back around to the mixing valve. And so again, you want it to be able to add heat to the loop because you don't want to have droop either. You want to maintain the temperature. That's the whole premise behind domestic hot water recirc, is that you're maintaining a temperature to eliminate wastewater and things like that, and so people can get hot water quickly. But you'll notice that there's this other drawing here down at the bottom, very similar to the drawing that we talked about with the two globe valves, but you'll notice that the globe valves in this scenario, they're not there. Okay. They are not there. You'll see that recirc is going to come back, it's going to split, and you're going to have check valves, which are great as long as they're in the right spot. And you're going to have a tie-in here at the cold inlet of the mixing valve. You're going to have a check valve just upstream on the cold inlet, and then you're going to have that other guy coming back here to the domestic hot water source, so it can feed right back into the hot inlet and make up for that heat loss in the loop. But again, no balancing now. You don't have to find that really specific scenario, so that way you can get it all set up properly. It's something that you can completely avoid and make your life a lot easier by going with a mixing valve that can prevent that altogether right from the get-go. So so definitely something to consider. Again, I wanted to talk about recirc creep because it's something that we get a lot of phone calls about, and many people that call, they don't even know how to describe it. They don't have words or a specific definition for what's happening, but they give me the symptoms and they say, well, this doesn't make any sense. This mixing valve must be bad. It's not really the mixing valve, it's just the fact that it wasn't piped and set up properly. And again, it can be all avoided either through proper piping and balancing or through the use of a different mixing valve that will eliminate it altogether. So again, recirc creep, very important. Nobody wants to get scalded, nobody wants to get sued, nobody wants to get hurt, nobody wants to hurt anyone. So let's avoid that altogether and keep on moving here. So the next thing that we wanted to talk about is going to be differential pressures. And this is something that's called out in everybody's manuals for mixing valves. This is just a particular little snippet from our 521 series MixCal, where we call out the fact that you need to have a maximum inlet pressure ratio for optimum performance, or up to a maximum inlet pressure ratio between the hot and cold. Now, what does that mean? We call out a 2-to-1 there, okay? So let's take for round numbers that you've got 60 PSI coming into this house or this building or whatever the case may be, and somehow you're managing to get 25 PSI at the hot instead of 60 PSI like you've got at the cold. So you've got this disparage, this big difference here between the hot and cold inlet, and you are exceeding that 2-to-1, and that is obviously a problem. But why is it necessarily a problem? The fact is that the mixing valve, in order to work and perform properly and work well, those pressures need to be as equal as possible, because the more of a difference there is, the less effective the mixing valve is going to be, and the less resolution it's going to have as far as making its adjustments and everything like that. And you're going to start getting some erratic temperature changes in there as well. But the biggest one typically we run into is the fact that the mixing valve just doesn't give me hot water anymore, okay? Maybe it's instead of 120 degrees, it's giving you 105 or 95, but you know full well that your domestic hot water source is sitting at 120 or 140. So how does this happen? And this is a pretty quick and easy one, but it's something that we get a lot of calls about, and it's something that I think that it's easily prevented here. But how does this happen? Typically what you're going to find and how this is going to happen is going to be plugged up heat exchangers. It happens all the time, okay? You've got dirty water, you've got scale capabilities or scaling properties, or magnesium and calcium in that water. It's going to scale up those heat exchangers, whether it be a flat plate heat exchanger in a combi boiler, whether it be a plate and frame for a larger commercial application, or in the particular case with the New England market, we see a lot of these tankless coils that are in cast iron boilers. And again, what happens with these guys is, these tankless coils or these flat plates, they have really tight passageways, and if you're not treating your water, what's going to happen is it's just basically going to start plugging up over time. And so tankless coils is a big one that we see, again, mostly in the New England market, but it's something that you want to avoid on all accounts. So I know most of the combi manufacturers and the tankless water heater manufacturers are very vocal about maintenance and flushing out these guys and cleaning them out appropriately, on the annual basis or even twice a year basis. So make sure to do that, because again, the more pressure drop you get across that domestic hot water source, the less capabilities, the less effective the less effective your mixing valve is going to be, is what it's going to boil down to. And this is something that, again, we get quite a bit of calls about. So make sure that you have provisions with, whether it be a tankless coil or a plate heat exchanger, to flush those guys out. Most of your tankless units and combis are going to have flush valves, or you're going to get them as an option, so you can flush those guys out with the appropriate cleaners. Now, the next one that comes into play a lot, and I do mean a lot, is sizing. Oh my gosh, if I had a nickel for every time somebody sized a mixing valve based on pipe size, I'd be a millionaire and I could retire and I would share my wealth with all of you, okay? But that's not the case. I don't get a nickel for every time. I just get a phone call every time that the mixing valve is not sized properly. Now, the first thing everybody wants to do is size it based on the maximum load, the maximum flow requirements of the system. So it's not typically so much a problem with residential applications, unless you start getting into those larger residential applications that might as well be commercial. But you get a commercial application, you're going to take account of all the fixtures. You're going to get all the fixture units. You're going to weigh them all out and everything like that, and you're going to put that fixture count up against what is referred to as a Hunter's curve. Now, here's the other fun part, is that Hunter's curves are, they're based on data that's very, very old, and we've got a lot lower flow fixtures these days. We're trying to conserve water and energy and all this other fun stuff. if you're going based on Hunter's curves, chances are you're going to be oversizing your system by quite a bit. And I think a perfect example of this, if you guys were not on for it last month, we had Peter Skinner and Gary Klein on, and they talked exactly about this exact scenario here, where if you're going by the book and you're sizing it, the way you were all taught and everything like that, your chances are you're oversizing it by a huge degree. Okay, and it, again, if you didn't have a chance to watch that webinar last month, they do get recorded, as will this one. We put them on YouTube. It's really eye-opening. They had a scenario with this. I believe it was a kind of an assisted living or an elderly, I don't want to say old folks home, but you know what I mean, place for older folks to go and live, and the actual water demand from these buildings was so minimal. I mean, it was just unbelievable, to the point where it was just laughable at how big the piping was supposed to be versus how big it actually was. So you're sizing this based on maximum flow requirements, and chances are you're oversizing it to begin with, which leads you to a whole nother problem. Okay, obviously you want to size it appropriately to make sure that you're meeting the maximum requirements for that building. Chances are you're going to be oversizing it, but the thing you need to remember is about minimum flow requirements. Okay, this is the phone call we get probably more than anything. This is the phone call that we get, the dreaded phone call. Okay, the one that scares me the most is the phone call that we get where we say, somebody says on the phone, and gladly we don't get too many of these, but they start the conversation off with, I've replaced this valve 3 times and it's still doing the exact same thing. And I gotta listen, I gotta hear them out and everything like that. But my first thought is that obviously the common denominator here is not the mixing valve anymore. Okay, you've replaced it 3 times. Let's look somewhere else, and that's why they're calling, obviously. So we want to help them out, but minimum flow requirements is typically the biggest reason why we get these phone calls. And I will tell you that every mixing valve under the sun, whether it be a tiny little mixing valve or this great big mixing valve, they're all going to have minimum flow requirements. And the general rule that you can think about is the larger the mixing valve, the larger the minimum flow requirements are going to be. So we've got our little under sink mixing valve here for our single sink applications. We call it our sink mixer. It has a minimum flow rate of 0.35 gallons per minute. This is perfect. It works great for your single lavs. It'll work great for your single temperature touch sensor faucets and things like that. But then you work into like our high flow thermostatic mixing valves. This is going to be your point of distribution mixing valves. And you'll notice that the 1 inch and 1 1/4 sizes are going to have a minimum flow of 4.4, and on 1.5 inch and 2 inch, 8.8. Okay. You're not going to get that from a single lav. You're not going to get that from a couple of lavs, even a shower thrown in there, chances are. So, how do you deal with this? And even worse, you get into the Legio mix, you get into that big 3-inch monster that's flanged and can flow enough for an entire city block. Okay, it has a minimum flow requirement of 22 gallons per minute. Okay, so again, how do you make up for this? How do you do that? Okay, there's a couple of ways that you can do this, and here are the solutions. The first one is going to be, instead of a single mixing valve, you are going to look into a high-low type mixing valve configuration or an assembly. Okay, this is an assembly that's going to allow you to use a small mixing valve. You've got the little guy right down here, and then a larger mixing valve. And during low flow applications, that smaller mixing valve is going to basically do all the heavy lifting. Okay, but as the pressure drop increases, because the flow is going to increase, the pressure drop is going to increase as well within this small mixing valve. And then on the outlet of this larger mixing valve, you're going to have a pressure reducing valve. So as the pressure drop increases across this little mixing valve, this big pressure reducing valve here is going to start opening up and allowing flow through this larger mixing valve to basically act as like a stage 2 or second stage in order to fulfill the needs of that building. Now, what's great about this scenario here is that this big mixing valve here can handle 40 gallons a minute, okay, at a maximum. This little guy here can only handle 10, okay, but the difference is that this big guy up here has a minimum flow of 4.4, which is obviously not attainable in many cases with a single lav or multiple lavs, but this little guy down here has a minimum flow requirement of 1 gallon per minute. So now you actually have the ability to have accurate control from 1 gallon per minute all the way up to 50 gallons per minute with this high-low assembly. And these are very common. Okay, this is not abnormal or anything like that, but this is another one of those scenarios where it's just a little bit different, and you're going to have to set these up properly. Okay, just like the recirc that we were talking about about before. And this is where a lot of times good intentions fall flat on their face, okay? The big thing here is that you have to be able to set up this pressure reducing valve to open at the correct time or at the correct pressure drop, okay? And so there's actually a procedure, and it's not quite as intricate as like the recirc balancing that we talked about earlier. But the fact is that you've got to set this guy up, and you've got to produce a demand in multiple scenarios and have certain valves valved off and things like that. So you want to have this valve to where it's going to start opening up at that just perfect time. Like when this valve here is, you know, starting to reach about 8 gallons per minute or 9 gallons per minute, and then, you know, this pressure reducing valve is going to open up and then start taking, you know, that big guy in there, and letting it go the rest of the way up to that 50 gallons per minute. So you can also even field assemble these high-low assemblies as well. Just something to bring up. I don't know the name of this very happy gentleman, but I can appreciate his hard work here. He did a really nice job. This was before Caleffi started introducing pressure reducing valves into the North American market. So he had a couple of our mixing valves paired with one of our industry colleagues here on a pressure reducing valve, and same idea. Little guy handles the flow to a certain point. Pressure reducing valve opens up because the pressure drop gets too great. Big guy takes it the rest of the way, and he's actually got 2 of them for 2 different systems here. So, or they're actually tied in all together, excuse me, but 2 high-low assemblies all tied in there. So again, this is one way to do it. Minimum flow requirements, if you're not, and let me backtrack here a little bit. If you're not meeting minimum flow requirements, I completely skipped over this. If you're not meeting minimum flow requirements, what's going to happen? Okay, what's the bad news here? Okay, if you're not meeting those minimum flow requirements, you are going to get unstable outlet temperatures. And again, the phone calls that we get where the guy says, I installed, this is the 3rd one, the 2nd one I installed, I put it in, I tested it, everything worked great. Okay, now again, if you're not meeting minimum flow requirements, when, you know, say that installer is no longer there anymore, if you're not meeting minimum flows, you're not going to get enough turbulence inside that valve body to create a good mixture and get a good reading from that thermostatic element or from the temperature sensor on, say, an electronic mixing valve. And that element or the sensor is going to see all hot or all cold, and it's going to hunt, and it's going to bounce all over the place, and it's going to be cold, it's going to be hot, and it's going to produce unstable outlet temperatures, which is obviously something you want to avoid. And so again, by replacing it, in a lot of cases, they'll open up a number of fixtures, and they're going to make sure that that thing works under the worst case scenario. They want to turn on all those faucets and everything like that, but that's not their demise. Their demise is going to be when that one single lav turns on, and then all of a sudden it's 80 degrees, and then it's 140 degrees, and then it's just bouncing all over the place. So you need to make sure that you're meeting those minimum flows, and one way to kind of go around that is with that high-low assembly. But another scenario and another tick in the box for continuous recirculation is this scenario as well, with minimum flow requirements. Okay, if you have your recirc piped properly, balanced properly, set up properly, and everything like that, the recirculation can make up for that minimum flow requirement of the mixing valve. So instead of having a high-low assembly, you could have a single mixing valve with your recirc running all the time, and everything's going to be perfect. Okay. In another scenario, I mean, again, you know, we talked about Legionella. Okay, running that recirc all the time, you're going to be able to help manage that Legionella risk to some extent, because you're going to be eliminating that stagnant water condition as much as possible. So, and even just kind of a couple of notes here too, you know, we all know that building code and code requirements and stuff like that are based on occupant safety first and foremost, and then, you know, you start talking about energy savings and things like that. But in all reality, occupant safety is going to trump energy savings any day of the week. So much so that OSHA has actually come out and condemned the use of aquastats on domestic hot water recirc, in citing ASHRAE 188, which is a standard on Legionellosis risk management and things like that. And not only did they come out and condemn aquastats, but they went so far as to say that pumps should run continuously and should be excluded from energy conservation measures, which I think is a pretty strong statement. And hopefully that all comes true, and the use of aquastats will go the way of the dodo there. So again, whether it be a high-low or continuous recirculation, again, that continuous recirc, if it's meeting the minimum flow requirements for the valve, you don't have to have that huge demand from the fixtures anymore. You can count on that recirc to meet that minimum flow for you. All right, now another one that we want to talk about here is CV. You'll probably notice this on pretty much every valve in the market, okay, whether it be a mixing valve, a balancing valve, a zone valve, a ball valve. You're probably going to find a CV value. But what is CV? What do you do with it? How do I use CV? Okay, CV, and I'm just going to read it right off here because I think it's the perfect way of describing it. It is a measure of efficiency at allowing fluid flow. Okay. CV, when you look at that number, that CV that's going along there, it's a coefficient, and it's going to tell you the gallons per minute of water that you're going to get at a 1 psi pressure drop through that valve. So you look at this little guy over here on the left, this 521 series mixing valve, it's going to have a CV of 3. So that's going to mean that you're going to have a 3 gallon per minute flow rate at a 1 psi pressure drop. Now, that does not mean that you can't go over 3 gallons per minute, okay? It's just kind of, think of it like a benchmark. It's like a rule, a quick, easy way to look at 2 different valves, okay? And say, like, this one has 3 and this one has 7, and this one can obviously flow more with less pressure drop than this one. And you can even see it here between the 2 mixing valves here, our 521 series and our 5231 series, okay? The difference between 3 and 7 is obviously pretty significant. And again, you're gonna get more flow through that bigger valve, that 7 CV valve, with less pressure drop, and that's perfect. Okay, so how does this come into play? I mean, we talked about it a little bit ago about how sizing mixing valves based on pipe size, and that really gets people into a lot of trouble. Okay. This is a perfect example. We have a little bit of overlap in our 2 models here with our 521 and our 5231. We have a 1-inch mixing valve in our 521. We have a 1-inch mixing valve in our 5231 series. And the 521 is a standard mixing valve. The 5231 is a high flow mixing valve, okay? But you'll notice that they're both 1-inch connections, but one is a 3 CV and the other one is a 7 CV. Now, this is where people get into trouble. They call up the wholesaler and they say, hey, I need a 1-inch mixing valve. And the wholesaler says, well, let me look for you. Let's see what we've got for you. Okay, I've got this mixing valve here, this 521616A. Okay, this will be your 3/4 inch press, or 1-inch press, excuse me. And then I've got this 523168A. This was 1-inch sweat, but they also have it in press too. Okay, and the wholesaler, maybe he knows, maybe he doesn't know, but the contractor doesn't know. They're just on the phone. They say, well, what's the cost? Okay, and this is where people are going to really step in it. Okay, the fact is that by going from this 521 up to this 5231, you're going to have a pretty big price difference. Okay, and luckily I'm the technical guy, so I don't have to talk about prices too often. But this is again where somebody's going to get themselves into trouble. They're going to say, well, why would I want to spend a lot more on this one when I can get this one for a lot cheaper? Okay, and this is where the problems come into play, is that maybe this mixing valve has the same pipe size connection, but it's not necessarily the same flow capabilities as the 5231, and that's where you're going to get in trouble. So we've got a little sheet down here, and I don't know who actually made this particular sheet. It was an Excel spreadsheet, but if you want it, make a note in the comments there. We can send it to you. This is a sheet where you can plug in just some basic numbers and find your CV, find your flow rate based on pressure drop and the CV of a valve, and find pressure drop and things like that, find flow requirements and everything here. So just to kind of go through it again here, at a 1 psi delta P with a 3 gallon per minute flow rate, you're going to have a CV of 3. That's this guy right up here, the 521 series. Now, if you take that 521 series and you take it up to its maximum, okay, its absolute maximum, you can get 13 gallons per minute through that guy, and we max out our mixing valves at 20 psi delta P, okay? So you take that 20 psi delta P, you plug in that 3 CV on this spreadsheet, it's going to pop up with 13.42 gallons per minute, which is pretty common with 1-inch copper piping for your domestic hot water systems, okay? But here's what's not common. It's not common to have a 1-inch system like this and a 1-inch domestic hot water system and then have a 20 PSI differential across your valve, okay? In many scenarios, engineers will really shake their head at that. They're usually looking for a 5 to 10 degree pressure, or 5 to 10 PSI pressure drop across that valve, and usually no more. So if you have 45 PSI coming into this mixing valve, you're gonna have 25 PSI coming out. And obviously that's a problem. So you want to avoid that if at all possible, especially you start looking into those big raining showers with the body sprays and all that other fun stuff. You want to make sure to limit that pressure drop. Now, you take in this next scenario here, you've got a CV of 7, which is this big 5231 series valve here. You take that same flow, 13.42 gallons per minute. again, not unheard of for one inch copper piping. And now all of a sudden, instead of getting a 20 PSI drop, you're getting a 3.68 PSI pressure drop, which is very, very manageable and much more it's something that you're going to want. It's not out of this world as far as the pressure drop. So definitely consider this. Again, I think the biggest thing to stress here is that to not size necessarily your valves based on pipe size, but to figure out exactly what your flow requirements are. And I know that can be a real trick on some of these jobs, especially older jobs that have been remodeled a zillion times. But there are water demand calculators out there from IAPMO. You can talk to an engineer. And an engineer especially can go through and count the fixture units and figure out what you actually need. It gives you a little bit of protection there from liability because you've got somebody in there designing that system. Just don't go, shoot from the hip and say I need a 2-inch mixing valve, because maybe this building has been repurposed for whatever reason, and maybe they used a lot of water before, but now they don't use a lot of water anymore, and now all of a sudden you've got this giant mixing valve in there for an occupant in this building that doesn't need all that water and doesn't need that big huge mixing valve. So again, just be really careful with that guy. All right, now the next one that comes up is temperatures, inlet, outlet. Why is it working? Why is it not working? And things like that. So, just again for round numbers, say you want 120 degrees to come out of a mixing valve. Okay, every mixing valve is going to have a minimum temperature difference between the hot inlet and the mixed outlet for that optimal performance, is how we note it there. And you'll notice here with our angle mix, our 520 series angle mix, we have a minimum temperature difference of 18 degrees. Now that's not to say that it's not going to work with a temperature difference that's a little bit lower, say 15 degrees or 14 degrees. I have found that some of these numbers are a little bit on the conservative side, but in order to get the most effective and optimum performance out of that mixing valve, that 18 degrees is something that you're going to want. And where the phone calls usually come into play is the fact that they've installed this new domestic hot water system, a storage tank or whatever, or a water heater. They put this mixing valve in and they're not getting 120 out of it. Okay, now I'm here to tell you that mixing valves do not produce hot water. They're working with what they've got, and it's one of those things where if you don't have the hot water in your water heater, it's not going to be able to magically make hot water. So definitely check your input temperatures. So in this case, if you want 120 out of that angle mix there, you're going to need roughly about 138 coming into that mixing valve in order to do that. And where we usually run into these phone calls is with a recent setting of like an electric hot water or electric water heater, or even worse, a heat pump water heater. So we all know those electric water heaters, they have a longer recovery time, and heat pumps even more so. You're lucky if you get a hot shower the next day in some scenarios, unless the backup is turned on. But just something to consider. It's something that we get a lot of phone calls about. People set the tanks to 120, and then all of a sudden they're not getting 120 out of the mixing valve. They're getting 112 or 105 or whatever, and they're like, well, what's wrong with this thing? Well, again, you need to make sure that you're putting slightly higher temperature than what you're looking to get out of that mixing valve. And I think this is a win-win for everybody, because by increasing that temperature of the tank, you're going to have the ability to extend the capacity of the tank. You're also going to have the ability to kill off bacteria, Legionella bacteria in that tank by running it at a higher temperature. It's a win-win all around. Okay, so make sure you're meeting that minimum temperature difference from hot inlet to mixed outlet. Now we also have some requirements there too for some of the little guys here too. The under sink mixing valves, our sink mixer again here. This one is going to have that temperature difference from hot inlet to mixed outlet as well. But what we also note in here is a minimum temperature difference between hot water inlet and mixed water outlet to ensure thermal shutoff function. Okay, 18 degrees here. And what does that really mean? So this is an ASSC 1070 mixing valve. This is an point of use mixing valve. This is going to go underneath your faucets. It's going to be the anti-scald mixing valve that we all talk about. Okay. The idea with this valve is that it has the ability to completely shut off the hot side in the event of a cold water failure, a shut off of the cold water for whatever reason. Okay. Again, preventing scalding, preventing anybody from getting hurt. But in order for that thermal shutoff function to work, you need to have that temperature of the hot inlet 18 degrees higher than the desired mixed outlet temperature. So if you're setting this sink mixer to 110, and you want that thermal shutoff function to still work, you need to have roughly 128 degrees coming into that guy. And then again, this is not just a Caleffi mixing valve thing, this is everybody's mixing valve thing. And again, it's something that you want to watch out for there too. So, and there's also some requirements too between cold water inlet and mixed water outlet desired temperatures that you want to maintain a differential there as well, because obviously, again, it's working with what it's got, and if the cold water inlet's too warm and you know, it can't cool the water down, it's gotta work with what it's got. So make sure you're abiding by these and making sure that you're doing that properly, because again, these are the reasons why we get phone calls, why people call us up and say, hey, I don't think this thing is working properly, and it's not the mixing valve's fault, it's just a product of its environment, and it's something that we got to avoid. All right, now last but not least, water quality. Oh my gosh, we talked about water quality a little bit before with heat exchangers. Water quality is something that is going to plague literally every single component in a domestic hot water system, and the most common one to really take the heat for it is the mixing valve. And so if you've got hard water, you're going to know it. If you've got nasty water, you're going to know it. Chances are you worked in that municipality before, you've worked in the building before, you've changed out faucet cartridges and shower valves and cartridges and everything like that, and you know it's going to go bad. So don't think that the mixing valve is just completely impenetrable when it comes to scale and debris, okay? Don't think it's bulletproof. We make our mixing valves at Caleffi to withstand corrosion and scaling as best we can, but I've never met a completely 100% bulletproof mixing valve, okay? They're all going to have a point where they're just, it's not gonna work anymore. They can no longer go on, okay? And in some cases it's a few years, in some cases it's 10 years, and in certain cases like this one was 6 months. Okay, and you can probably see it right here, lasted, and then over here 6 months. Okay, this guy here, it was in probably one of the worst scenarios. Now we all know that magnesium and calcium, it wants to precipitate out of solution as the temperatures get higher. That's why you got scaling. That's why your 40-gallon water heaters turn into really giant boat anchors, because they're filled halfway up with sediment and debris and everything like that and scale. That's why you have these water heater graveyards and these old farmhouse basements, because nobody wants to take them back up the stairs. And again, same thing holds true with your mixing valves. If you've got hard water and you've got the potential for scaling, your mixing valve is going to be susceptible to it as well at some point. And in this particular case, they told me that it lasted 6 months. I can't confirm or deny that. Okay, I can only go based on what they told me. They sent it back. They said, hey, it's not working. I opened this guy up. I said, well, what were you doing with this thing? And what they were actually doing with this thing is they had it on the outlet of a heat exchanger for domestic hot water. On the other side of the heat exchanger was connected to a steam system, and that steam system was obviously very, very hot, and the water that was coming out of that heat exchanger was very, very hot, and it scaled. And it is what it is. Okay, so with that in mind, again, if you've got your potentials for issues with your domestic hot water, it's something that you're going to probably know about already. So definitely keep it in mind when it comes to your mixing valve. Okay, now that could mean either that you are cleaning the mixing valves, like our mixing valves, for example, we don't do replacement cartridges. We have replacement bodies available with them. But maybe say you've got this mission critical application that they call up every 6 months or every year or whatever, and oh my gosh, the hot water is not working, you need to get here right away and everything like that, and it's always my pants are on fire and we need this done right now. That would be a perfect scenario to look into keeping a second mixing valve on site. Okay, and we've seen this done in many scenarios where it's, again, that mission critical application. They keep a second mixing valve on site. They do a hot swap once a year on a preventative maintenance schedule. So you're not working around this person who's frantic because they don't have hot water. You're working around a preventative maintenance schedule. They take out that mixing valve that was in there for a year, they clean it all out, and then they just leave it sit there and they wait until the next year and they do it again. Okay. Now I stole this picture from Bob, so I hope Bob doesn't mind. He rigged up this little contraption here where he was using a domestic hot water, a tankless coil cleaner, a descaler kit from like a tankless water heater, and he used a Y hose here and ran it through that mixing mixing valve to clean it out, and that's perfect. Okay, you know, you've got a mixing valve there, you can do that quick hot swap. We've got the unions on our valve, you can pop them in and out really quickly, clean up that one that you just pulled out and leave it sit there, wait, and again, do it the next time, the next year, and keep on going. I've had other applications where they put two valves in parallel, and they kind of do them a lead lag kind of scenario. They'll run this one for 6 months and then valve it off, and then they'll run this one for 6 months, valve it off. Same idea, you know, you can take those out, clean them up, do whatever you got to do, and it really prevents a lot of those issues. And again, we've got some pictures over here of scaling. If you know you've got scaling, you know it. This was actually a 3/4 inch recirc line that turned into roughly a 3/16 recirc line over here from North Carolina that I was able to see, and I believe this was a Bob picture up here as well. That's I believe it was a 3 or a 4 inch T. And again, your braze plate or your plate and frame type heat exchangers, they're going to scale up like crazy. So if you've got hard water, just don't think that your mixing valve is not going to need attention. This is something that needs to be managed, and putting it into the preventative maintenance schedule is going to be the best bet for you and your customers. It's going to be work for the service contractor. It's going to be good for the customers, because hopefully you're nipping in the bud before it becomes a problem, and you can be the hero. So definitely consider that. Water treatment, you know, obviously goes hand in hand with that as well. So you know, all good things to think about when you're talking about poor water quality. All right, now let's just quickly summarize what, you know, we talked about creep, and we talked about droop, we talked about pressure drop, we talked about, you know, sizing of mixing valves. Again, oversizing a mixing valve can be just as detrimental as undersizing a mixing valve. We talked about CV and how you can kind of use that to compare mixing valves, or again, any type of a valve, whether it be a zone valve or a balancing valve or whatever. You know, you can use that as a good benchmark. And we talked about your domestic hot water source as well as your water quality. So I'm going to open up the floors here, and Max, I don't know if you're still there. Do we have any good questions from the guys? I know I talked really fast and I burned through my entire hour here, but maybe we've got some good ones that we can finish up with here.
Yeah, we've got a couple questions that are a similar topic. So if you had a recirc creep issue and then just added a thermal balancing valve to the recirc loop, is that going to fix everything?
Ooh, that's a good question. So your thermal balancing valves are a dynamic balancing valve. They are not going to be a fixed flow type balancing valve like what you're going to find with your manual balancing valves there. So a thermal balancing valve is potentially going to help, because as the temperature starts to come up, it's going to start to close off that balancing valve more and more. But the thing is that thermal balancing valves, they never close off 100%. Okay, so you're still going to get flow through there. So it's one of those kind of maybe not scenarios. There's no 100% proof there that it's going to completely eliminate the scenario. It can't hurt, but in the same breath, I can't guarantee it's going to fix it 100%.
Yeah, I guess it would depend on the heat loss of the recirc loop a little bit too. And I think
a lot of variables.
Diagram right there is kind of the perfect example of a thermal balancing valve, instead of just having one to the right of the recirc pump to fix that problem. Then what are some other general recommendations on limiting energy loss due to continuous recirc? So what are some other things you can do to help?
Oh, well, you know, we just talked about it. Thermal balancing valves. You couple, you know, the thermal balancing valves, again, being a dynamic balancing valve that are going to open and close based on requirements of the branch or the riser or whatever the case may be. As the temperature comes up in that riser or that branch or whatever the case may be, it's going to start closing off. It's going to start limiting flow. You couple that in conjunction with a variable speed circulator. That is really going to bring your energy consumption down to pretty much as low as you can possibly get it in a scenario where you're going to run continuous recirculation. Obviously, big single speed circulators with, you know, manual balancing valves that were never set up properly are going to be the the worst case scenario. But you look at thermal balancing valves that are set based on a temperature, not a fixed flow rate, in conjunction with that variable speed. I think that's going to be your best case scenario. Obviously, you're going to pay a little bit more upfront for that kind of a setup, but you're going to have a lot easier time setting those balancing valves, and that customer is going to enjoy the energy savings for the life of that building, or at least the life of the circulator.
Okay, and then I've got another one that, let's say you've got a large hot and cold pressure differential, and you're using a mixing valve with check valves, Is there a scenario that you could have flow through where the cold water would flow into the hot water system?
Well, if you've got check valves at the inlets of the mixing valve, and that's a good point too. And there was actually a question in some of the pre-submitted stuff about recommending additional check valves for preventing cross flow through a mixing valve. So I'm gonna go off on a bit of a tangent here, but per ASSC 1017, check valves are not a requirement for 1017 mixing valves, but we do have to recommend it. Okay, so your ASSC 1017 mixing valves we have to recommend having check valves for potable applications or domestic hot water applications. Now, if those check valves are in there, obviously it's going to prevent cross flow from one side to the other. Now, it's still not going to help that mixing valve work any better if there's a huge difference between hot and cold pressures. You know, say it's 60 on one side and 20 on the other side, kind of thing. It's not going to help that scenario, but it's going to prevent the migration from one side to the other. Is that a good answer there?
Yeah, I think so. I think that
Yeah.
unless there's like a copper shaving holding up that check valve or
Sure.
something, if that's
Sure.
not seating properly, that could be an issue that you'd have.
Yeah, and I mean, if you've got crossovers anywhere else in the system too, you know, if you've got that big pressure differential from one side to the other, I mean, if you've got any other, say like single handle faucet cartridges that are failed, or maybe you've got a point of use mixing valve, again, with check valves that have failed or have debris in them or anything like that, that's going to prevent it's going to, you know, allow migration from one side to the other and cause issues there as well.
And then we've got one kind of general question here at the end. Should every hot water system have a recirc line?
Ooh. You know, I'm going to speak from my personal perspective here. I live in a long ranch home where the mixing or the water heater's on one end of the house, and I've never timed it, but if you ask my wife, it takes roughly about 3 hours to get hot water from one end of the house to the other. But with that in mind, it's one of those things where I'm just kind of on the fence. It's like, you know, but you know, I know that there are code requirements where if it's over a certain amount of time or a certain feet from, you know, to the furthest fixture, that recirc is required. I think, you know, recirc is definitely something to help save water and help, you know, makes everybody happy when they can just turn on the faucet and the hot water's there. You know, you don't have to sit and wait for it. But you know, in the end, I think it's a code thing. I think it's a great thing to have even without code, but it's all kind of personal preference there in a lot of cases.
And I think that it depends on the state that you live in, and if you pay more for
Yes.
water, if you pay more for energy.
Bingo. Yeah.
Outside of the code requirements, those might be California might be more wait time sensitive than other places because they don't want to waste the water. So
Yep. Yeah.
And I think oh, go ahead.
Well, I was going to say I had one question in here that was in the pre-submitted that I thought was a really good one. And what they wrote here was, is there a need for a bypass loop, or is it recommended to have a bypass loop around the mixing valve? Okay. And I've seen this done many times. I don't know if certain areas don't like it based on code, because obviously if you opened up that bypass, you could let full hot water, you know, 140-degree water out to the mixed outlet side. But for maintenance purposes, man, that bypass is a breeze. It's awesome. I mean, obviously you're going to take down your tank temperatures or your storage temperatures, so that way you're not going to hurt anybody. But you can roughly, I mean, you can take that mixing valve out of the scenario if you've got it isolated. You open the bypass, and you can do the service and maintenance to a mixing valve without having to take down the entire building, which I think is a huge benefit. But you know, again, certain areas may frown upon that. Some areas might okay it, but then you got to take the valve off, or the handle off the valve. I mean, there's all kinds of things there. So, you know, if you can get away with it, I would be all right with it. Like I said before too, I've had plenty of customers where they do two of them in parallel, and it's two mixing valves in parallel. And it's not because they need the redundancy or that they need the higher flow capabilities of two mixing valves. It's because they wanted to do a lead lag, so that way they can do maintenance on one while keeping the building operational and not having any interruptions in service. But yeah, so, and there was another couple good questions in here too. Some of these get pretty far off into the weeds, as you can imagine. You know, we leave this opportunity for questions rather open-ended, and some of them are better left for a phone call or an email. So again, if you have asked a question during the webinar or in the pre-submitted questions, I will be getting back to you, and we will make sure that you get your questions answered to the best of our abilities. And if we don't know the answer, we'll point you in the right direction. But unless you had anything else, Max, let's go through these last few slides.
Sounds good.
Alrighty, so again, if you have any questions too that you want to make sure you get this all taken care of right now, you can contact our office in Milwaukee. We've got a great tech support team. Myself, Kevin, who's the director of product management and technical support, along with Dan and Greg. They are some real whiz bangs right there. They can help you with any of your technical support questions. All of us have field experience, and we can make sure you can get squared away really quickly. Also on the docket there, Greg and Dan have been doing podcasts, and I know podcasts, I haven't been a huge podcast guy, but they're growing on me, and Greg and Dan do a great job talking about various topics about hydronics and plumbing with their quick podcasts. They're typically around 15 minutes, so make sure to check those out on the usual places. And recently, I've been doing a little initiative called the 5 Things You Need to Know. It's a little mini series that we're doing. Again, kind of same idea as the podcast, but with a little bit of video flavor in there as well. We talk about, again, hydronic and plumbing applications and just some quick, real down and dirty type stuff that we can get you out the information that you need without flapping our jaws for an hour. So check that out on YouTube, as well as a lot of the different social medias. We are on all the social medias, so check us out there. Not only do we talk about new product launches and things like that, but we do have a lot of really cool contests throughout the year. We let you know when upcoming webinars are going to be happening. We also do giveaways and things like that. We talked about those NIPEX sets that are going to be available from the Shop Talk webinar on Monday. A lot of good stuff on there, a lot of good fun. And also, I would encourage you to get on those social medias and send us your pictures of your installed product. We love to see that stuff. We love to see how our products are being used. We love that you like to show it off. So definitely share it with us on all those social medias. And without further ado, again, appreciate everybody's time. Thank you, Max, for supporting me here with all the questions and everything like that. And I hope you guys have a great rest of your day, a great Friday, and a great weekend.